Continuing where we left off, we are looking at the convergence and divergence of this sequence, negative 1 to the n plus 1 over n squared plus 2. This is for our Calculus Chapter 9 practice test. So we're going to try to find the limit if this sequence converges, and of course by definition it has a limit. And if it doesn't converge, then by definition this sequence is going to diverge. I look at the sequence and I see that negative 1 to the n power, and I'm always looking out for that piece because that negative 1 to the n power means that this sequence is going to be an alternating sequence. And that's useful to me because for an alternating series, either the limit is 0 or it does not exist. It's going to be sufficient for us to look at the limit as n approaches infinity of the absolute value of the sequence. And that's the same thing as the limit as n approaches infinity of n plus 1 over n squared plus 2. Basically, we don't need the alternating factor here, the negative 1 to the n power. If we just take that out of our explicit formula, then we are going to produce a series, a sequence that only has positive terms. I look for the highest powered order of n, which is n squared. And then I multiply the numerator and denominator by 1 over that highest powered term. So 1 over n squared. So this is the same thing as the limit of 1 over n plus 1 over n squared, the whole thing on top of 1 plus 2 over n squared. Now I'm going to go over this really the long way here, and eventually, of course, we can look at the short way. But if we have the limit of two things being divided, a numerator over a denominator, that's equivalent to the limit of the numerator divided by the limit of the denominator, provided, of course, that the limit of the denominator is not equal to 0. Well, if I have the limit of two things added together, well, that's the limit of the addends added together, of each addend added together. And now that I have this, I can evaluate each of these really small pieces together. So look at this, the limit of 1 over n, that's 0. Because the numerator is staying the same and the denominator is growing. Same thing for 1 over n squared. Same thing for 2 over n squared. But the limit as n approaches infinity for 1, well, there's no n in that expression, so that's just 1. So my denominator isn't equal to 0, so I was okay to use the division part of the limit properties. Well, 0 plus 0 over 1 plus 0, of course, that's equal to 0. And since we have an alternating sequence, then the limit of the alternating sequence is also equal to 0. Remember, the alternating sequence either has a limit of 0 or does not exist. So this sequence converges to 0, which is the only number that an alternating series can converge to. For number 5, we have find the formula for the nth term of the sequence 3 over 2, 6 over 4, 9 over 12, etc., etc. And my trick for this is to look at the numerator and denominator separately. Let's take a look at the numerator. We've got 3, 6, 9, and 12. So it looks as though the rule here is going to be add 3 to the previous term. This is indicative of an arithmetic sequence where the first term is 3 and the common difference is also 3. We saw before that the explicit formula for an arithmetic sequence is a1 plus n minus 1d, which for this sequence is going to be 3 plus n minus 1 multiplied by 3. So the explicit formula is an equals 3n. Let's look at the denominator. Now the first thing I would do is to check and see if this is an arithmetic sequence, which of course fails. Next thing I'm going to do is to see if this is a geometric sequence, which also kind of fails. But it fails in an interesting way because I can see there's a pattern here in these ratios. So the next thing I'm going to do is number the terms, and then I'm going to see if I can simplify each term. Now, I noticed right off the bat that each one of these terms is even. So I can divide each term by 2. Let's see if something emerges if I divide each term by 2. And now something interesting has happened, because if I take a look at the red numbers that I've highlighted here, that is the factorial sequence. Now, the factorial sequence is really a hard thing to train you to look for. You really just got to kind of memorize that sequence: 1, 2, 6, 24, 120. But once you do have that memorized, then you should be able to recognize it whenever you see it. So this looks like the next thing I notice here is that all the factorials match the term number. And now that I see that they've matched the term number, I am ready to write my explicit formula. So the denominator sequence, b, I'm going to call it b, that's going to be 2 times n factorial. And notice that we have also checked, we've also left the 240 out, so if we want to use that as a check, we could. 2 times 5 factorial is actually 240, so this sequence does seem to work. So put together with the numerator and denominator, we just need to put the general term for the numerator on top of the general term for the denominator. And that's 3n over 2n factorial. And basically, you should probably start getting used to the factorial sequence, because that is going to play a role in what we do, especially in Chapter 10. So for question 6, the last one we're going to do here in this video, we're going to determine if this sequence converges or diverges. And if the sequence converges, we're going to find its limit. So these questions are always kind of phrased backwards, because really we should be looking for the limit, and then based on the limit deciding whether or not the sequence converges or diverges. I'm looking at Bn and I'm seeing that it's not a alternating sequence, so I'm just going to straight up find the limit. So what is the limit as n approaches infinity of 2n minus 1 over 3n squared plus 1? Like on the previous one, number 4, I'm going to identify that n squared is the highest power of n in this problem. And then I'll multiply the numerator and denominator by 1 over n squared. That's going to give me 2 over n minus 1 over n squared over 3 plus 1 over n squared. These 3 sequences will go to 0, so this limit will be 0 over 3, or just 0. Since there is a limit to the explicit formula, this sequence is actually going to converge to that limit, so this sequence converges to L equals 0. And that's it for this video. We'll see you at the next one when we continue our Chapter 9 practice test.